In the topology given on the slide, router 1 can reach router 3 by two routes. The first route is through router 2, the successor for this route. This route has metric of 10 and RD of 5, which makes FD of 15. The second route is through router 4, the successor. The metric, therefore, will be of 10 and RD of 10, which makes FD of 20. Let us next discuss feasibility condition. A route is called a feasible successor, FS, if it satisfies the feasibility condition. This condition states if the route has an RD less than the FD of the current successor route, it can be an FS. This mathematical construct ensures a loop-free topology. Let us understand why. RD is the metric between the next hop router and the destination. FD is the metric for the entire route to a destination. The feasibility condition states if the possible new route's RD is less than the present route's total metric, the new route cannot be going through more network nodes and looping back on itself. The advantage of having an FS is, if the current successor route fails, the feasible successor will be installed in the routing table without rerunning dual. This makes convergence almost instantaneous. To complete the computations necessary, the topology database contains the successor, the FD, and any FSs with their RDs. There may be multiple feasible successors. The route with the lowest FD is entered in the routing table. We will discuss feasible successor in the next slide. Let us look at the topology again. As discussed earlier, router 1 has two routes to reach router 3. The route with router 2 as a successor has an RD of 5 and an FD of 15. The route with router 4 as successor has an RD of 10 and an FD of 20. Since the lowest feasible distance is through router 2, that route would be entered in the routing table as the best route. Is there a feasible successor? The answer is yes, because the route through router 4 meets the feasibility condition. RD10 is less than the FD15. Therefore, the route through router 4 will be entered in the routing table if the route through router 2 fails. In the next slide, let us look into a routing table. EIGRP separates routes into two categories depending on the origin of routing information. Internal routes are learned from an EIGRP neighbor in the same routing process. In other words, they have matching ASNs. All routes from another routing domain are considered external. This could involve another routing protocol, such as OSPF, or another EIGRP process. Remember that administrative distance gauges the trustworthiness of a route. EIGRP assigns an AD of 5 to summary routes, that is, routes that are manually summarized within EIGRP. Internal routes have an AD of 90 and external an AD of 170. Let us discuss how to configure EIGRP on a Cisco router. Two configuration modes are used for EIGRP. The most important is the router configuration mode. This mode is entered with a router EIGRP ASN command from the configuration prompt. The other configuration mode used is interface configuration mode, where many options can be configured. Metric, for example, is assigned by interface. Let us look at basic router mode configuration. EIGRP's ASN must match on all routers that you want to participate in the EIGRP process. Look at the syntaxes given on the slide. A router ID is defined in dotted decimal format, just like an IPv4 address. If a router ID is not configured, the router automatically selects one. If there is an active loopback interface, it selects the highest IP address on that interface. Otherwise, it selects the highest IP address on an active physical interface. We will continue this discussion in the next slide. Without an inverse mask, any interface that belongs to the classful subnet will participate in EIGRP. If you specify an inverse mask, any interface belonging to the specified subnet will participate in EIGRP. The network command specifies which interfaces will be enabled for EIGRP. If the address of an interface lies within the subnet defined in the command, that interface is EIGRP enabled. Note that an inverse mask is optional. As shown in the command, an ASN of 22 has been assigned. The router ID is in dotted decimal form. An inverse mask is the regular subnet mask subtracted from 255.255.255.255. For example, the inverse mask of 255.255.240.0 is 0.0.15.255. Let us next discuss automatic summarization. If auto summary is specified in router mode, then all routes are advertised as classful networks. This was the default before iOS 15.0. The default starting with iOS 15.0 is no auto summary. Therefore, EIGRP is now considered a classless routing protocol. It supports discontiguous subnets and variable length subnet masking, VLSM. We will next move on to equal cost load balancing. EIGRP has equal cost load balancing up to 4 paths by default. This means up to 4 EIGRP routes with an equal metric can be deemed the best route and be added to the routing table. For example, if 3 EIGRP routes have the same metric, there is a route ready to use in the routing table until all 3 fail. Dual does not have to run to find the next best path. Depending on the iOS and platform, the maximum number of routes can be changed with the command shown. Equal cost load balancing is preferable. However, EIGRP is the only routing protocol discussed in this course that also offers unequal cost load balancing. Let us look into unequal cost load balancing in the next slide. In unequal cost load balancing, EIGRP routes will be considered equal if they are within a certain variance of each other. The reason for this approach is simple. If one of the routes fails, the traffic is shifted almost instantaneously to other route or routes. No dual recalculation is required. Let us discuss how to configure this in the next slide. With the variance command, the following 2 conditions must also be satisfied for a route to be added to the routing table. Firstly, the feasibility condition must be satisfied, where the RD of the possible route must be less than the current FD. In addition, the feasible distance of the possible route must be less than or equal to the variance multiplied by the current route's feasible distance. A variance command syntax is shown on the slide, where the multiplier is between 1 and 128 and default is 1. Routes that are neither successors nor feasible successors can never be added to the IP routing table, regardless of the variance setting. Use the Show IP Protocols command to verify the occurrence of unequal cost load balancing. We will now discuss passive interfaces in the next slide. The command on the slide blocks routing updates from being sent out of the interface. If routing updates are not needed, perhaps because static routes are used, then using the passive interface command can save router protocol processing overhead on the router. Note, a router cannot become a neighbor if it is connected through a passive interface. Let us learn how to limit the EIGRP bandwidth usage in the next slide. EIGRP has a command shown on the slide to limit the bandwidth that EIGRP uses for processing. Based on the interface bandwidth on the Show Interface command, the interface will use up to the % of bandwidth specified. By default, EIGRP uses up to 50%. This command is configured to prevent EIGRP from flooding the interface, thereby limiting EIGRP overhead. Check the configured default bandwidth on the interface before using this command. Use the Show Run command to verify. In the next slide, we will understand manual summarization. Manual summarization can be configured anywhere in the network. This is a feature unique to all the routing protocols. Note that administrative distance is optional. The default is 5. We will continue this discussion in the next slide. Manual summarization works as follows. The summarizing router adds a route to its own routing table for the summary prefix and prefix length. The outgoing interface is set to null 0. This is called a discard route because a packet with a destination with a longest prefix match to a discard route is dropped. The advantage is it decreases the size of the routing tables of subsequent routers, although not that of the summarizing router. The disadvantage is it can cause suboptimal routing. Packets routed to inaccessible destinations will be routed to the summarizing router before being discarded. Now let us look at split horizon. By default, EIGRP split horizon is enabled on most interfaces. When split horizon is enabled on an interface, no update or query packets are sent out to an interface through which that packet came. This reduces the possibility of routing loops. For example, in the figure on the slide, if router 1 learns about the route 25.25.25.0/30 from router 3, then any updates or queries concerning that route will not be sent out to interface F01. Now we will look at the IPv6 configuration in the next slide. EIGRP is also available for IPv6. This slide shows an IPv6 configuration. Take some time to review the configuration and notes. Let us move on to the quiz questions to check your understanding of the topics covered in this lesson.